Okay, this is another video in the series for Math 1224 for UTSA. We are going to be doing section 2.5, physical applications, and we're going to start with the mass of a thin rod, which I will generally draw as a rectangle, we hope. There we go. Like this, I'll make it maybe start thin, and we'll usually start at 0 as the beginning, and then some length L, whatever, what do we have? Sometimes we'll say that this is from A to B, depending on the situation. So let's start by talking about constant density. So if I know that some say metal or wood or plastic rod is, I don't know, let's say I don't know, let's say 50 centimeters, so half a meter, right? And I know that it's 2 grams per centimeter, which I guess would be pretty light, right? Really thin metal rod. Well, if I multiply centimeters with grams per centimeter, I'll get grams, right? If I do 50 centimeters times 2 grams per centimeter, the way that units work is a lot like how fractions work. That's why we often use fraction notation. The centimeters cancel essentially, and I get 100 grams. Okay, so that's basically, here's how you see what's the mass of a thin rod. If you know the density, how many grams per centimeter, then, and you know the length, well, then there you go. What if we had a variable density? So if I had a thin rod that was, say, either because of the way it was made, maybe it's wooden and at one end it's denser than at the other end, or it's plastic and it's denser at one end, or maybe it's a composite material, right? It's made out of plastic and metal, or two kinds of metal, or two kinds of plastic, and one end is heavier than the other end, right? So let's say we had a rod of variable density. I'll represent it, I guess, like that, good enough. So let's say over here at this end, and you know what? Let's actually make it longer. Yeah, let's do that. Okay, good. So let's say over here at this end, the rod is 1 gram per centimeter, and over here it is 2 grams per centimeter. Okay, maybe it's made out of some sort of combination of plastics. Maybe there's actually it's a composite material, and maybe this section is heavier than the non-shade section, and the oh, did I say 2? I meant 5. And then the non-shade section is the lighter material, so it's not as dense, and it changes linearly. Let's suppose that. So that means that, let's say this was cut evenly, so 2, 3, 4, respectively. That means that this section here on average is 1.5 grams per centimeter, right? And let's say that the whole thing is, let's say 50 centimeters long. I think that's what the first example was, 50 centimeters long. So that means each section is 12.5 centimeters. So this first section right here, this is going to be 1.5 grams per centimeter, right, times, well, 12.5 centimeters, right? What is that going to be? 18.75 grams for that first section, right? And we'd say, oh, well, this section, this is going to be 2.5 grams per centimeter times 12.5 centimeters. So what is that going to be? Another, was that 31.25, I believe? And then this one's going to be 3.5 grams per centimeter times 12.5 centimeters. That's going to be 43.75, I believe. We'll check this in a moment. 43.75 grams. And this last section is 4.5 grams per centimeter times 12.5 centimeters. So that's going to be what, 56.25. Okay. You might have noticed what I could have done is to just add up these values and multiply by 12.5. So I'm going to check this with a calculator real quick. If I add up 18.75 plus 31.25 plus 43.75 plus 56.25, then I get 150, okay? So plus, plus, plus 150 grams. If I take those densities, 1.5 plus 2.5 plus 3.5 plus 4.5, and just multiply by 12.5, yeah, I get 150. Cool. So we don't have any mistakes here. So I can estimate, and that might not be the exact weight, or I should say mass, the exact mass, right? Because I'm assuming a fair bit now. Because I'm assuming that it changes linearly. It turns out I'm 95% sure it actually would be 150 if we take a more sophisticated approach to this. But how would a more sophisticated approach look? How much room do I have? Yeah, we got some room. How would a more sophisticated approach look? Well, I'm basically going to take the same thing, and I'm going to redo this by saying, well, there's some density function. Okay, so got my rod here. That'll work. Let's say that the density starting at, say, x equals 0, to say x equals, I don't know, let's say x equal, well, let's do from A to B. From A to B. Let's do it generically. And let's say that the density function, sometimes the Greek letter rho will be used, kind of looks like a p, so p of x, or we could use delta of x for the density function. This will give the density as a function of the position along the length of the rod. Okay, density function, which I'll abbreviate. So what I can do is say, well, if I chopping this up worked, why don't I chop this up into pieces? So let's go chop, 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 chop. Okay. So I'm going to say, oh, well, this is x I. This might be very familiar at this point. This is x I minus 1. Okay. And the length of that section, it's not 12 and a half. Trying to do a curly bracket and I'm failing. There we go. That's good enough. This is going to be delta x. It's the length of the bracket, right? And I can pick a representative part within the section to say, oh, well, what's the density? Because the density right here at this edge is going to be different from the one at this edge. Just like up here, the density here is 3 and the density here is 4. So I was saying, well, yeah, on average it's 3.5, right? In other words, I was picking the middle. I'll just pick the middle. I'll use that density to represent the whole thing, which sometimes will give you the exact value. Other times it will give you just an approximation. So let's say that we're getting an approximation. That's not the exact value. And I'm just going to say, well, let's pick some section. And I guess I'll use a different color here. Let's pick some section here. Maybe it's in the middle, maybe not. We'll call this xi star. We'll pick some representative section somewhere in that chunk to say, oh, the density there is going to be rho or delta, whichever one you want to use. Some books use rho, some use delta. Let's say that the density at x sub I, or at section I, right? So the density of section I is rho of xi star. And this is in, say, grams per centimeter. And it could be, whatever units you want, of course. So that means that the mass of section I is, well, that's going to be a rho times xi star delta x. Delta x is the length of the that section, right? And so that's giving us an approximation, just like we did, 3.5 times 12 and a half. Do the density times the length of that section, okay? So then what if I want the mass of the entire thing, right? Mass of the rod. Well, that's going to be the sum as I goes from 1 to n, the number of sections, right? Times rho of xi star delta x. And of course, this is an estimate. This is estimated, right? And so if we want the exact this is exact mass of the rod, right? Well, then we're going to want the limit as n goes to infinity. That way, when we make our slices, we're picking very, well, not very, but increasingly narrow slices so that when we pick our representative section, go, oh, well, the density is such and such. There's less error involved for each section because the longer your section is, and you just pick at random. If I were to pick this one to represent the entire thing, well, I'm picking the low end because it's closer to 3. If I pick this section, I'm sorry, this spot, well, I'm picking the high end. I'm gonna pick, like, my density will be almost what 4 would be, and most of it is not that dense. I'd be overestimating, right? Because I said this one increases linearly from end to end. And for some function that may not be linear, well, then how do you know where to pick? But if your slices are very narrow, then when you go to pick your section to say, oh, here's our representative, well, it's going to be more accurate because your sections are smaller, right? Kind of like when we go to make a Riemann sum to do an area, the narrower the slices are, the narrower the subinterval, the less it matters where you pick the height. Well, it's so narrow anyway, who cares? So the limit as n goes to infinity is the sum, so I goes from 1 to n of rho of xi star delta x. And of course, predictably, this turns out to be the integral from a to b of rho of x. And that's not a p, it's a rho, but I got a little bit lazy. This is a little bit better, I suppose. This is actually the best one. Dx. And there we go. This is how, if you have a density function that gives the density as a function of x, you could say, okay, well then, and you know the length of the object, well then what's the mass of the entire thing, right? So that's what we can do for a thin rod. Okay, so let's do an example of that with a variable density function. I just want to graph this real quick to give you an idea of what this density function looks like. You probably know, but it doesn't hurt to give an idea. So we're going to start with x equals 2, right? So let's say we're starting like right here. Well, then the graph going out to 10 more units, okay? I'm taking centimeters to be my units here. Something like that, right? So that's the density function. So at the left end, the rod is much denser than it is at the right end. But even in the middle, like this whole right half is about even density throughout. It's just far denser at this end, right? Like if you were going to make a tool, you might not care how dense it is at this end. Maybe this is where the handle is for a tool, but you need the density to be greater at one end because it's like a digging tool or a cutting tool. I'm just making this up, but there might be a reason you would want to do that. So in order to find the mass, I'm going to integrate from 2 to 12. And notice I'm not saying 2 to 10, right? I'm saying I'm starting at x equals 2, but the length is 10. So go from 2 to 12. Okay, well, the density function, so e to the negative x dx, right? And what I want you to think about is on this graph is the following. The slice I'm making where this is like this is x and the width is dx and the density is rho of x, okay? So the rho of x rather, this is in grams per centimeter, okay? X is a position along the axis, right? This is x and this is in centimeters. Dx is a distance along that axis. So this is also in centimeters. So what I want you to think about, struggling with that m there. What I want you to think about is the units involved, because the units can really help setting up your integrals when we get to the later, more complicated problems. This is in grams per centimeter. So in order to get grams or finding mass, we have to multiply with something that's in centimeters. Well, dx, this is in centimeters. And so we're going to get grams that way. Okay. So when you're building your integrand, with this one, it's not too hard. This formula is easy, I guess. But when you're building your integrand for a problem that's more complicated, keeping that in mind, what are the units involved? That can really help to do the setup. Okay, so this is going to equal, well, negative e to the negative x, evaluated at 2 and 12. So this will be negative e to the negative 12 power plus e to the negative 12 power. And there we go. That's our mass, although This is in grams, right? Often for these kinds of problems, we're going to want a decimal approximation because is that a lot? I'm guessing not, because exponential functions fall off very quickly. So e to the negative 12th is a teeny tiny number. And then even e to the negative 2 is pretty small. So I type this in my calculator. I'm going to get about 0.135. 0.135, and this is in grams. Okay, so there's our first example of a variable mass for a linear object. Okay, let's do another example. Let's say we are finding the mass of a rod of length 5 centimeters starting at x equals 1 with the density function rho of x equals 1 over 3x minus 2 grams per centimeter. As before, I'm just going to do an integral from 1 to, pause the video and think about from 1 to where? How far are we going? Okay, so we're going 5 units in length, so we're going to go up to 6 because that would be 5 units from 1. Of the density function 3x minus 2 dx. Again, remember, this is in grams per centimeter, and this is in centimeters, right? And so the product there is in grams. So I'm adding up small slices of the rod, the mass of the rod, right? I have the first small slice, the second small slice, the third small slice, dot, 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 all the way up to the nth small slice. And each one is a gram measurement. Okay. So this will be, well, 1/3 ln 3x minus 2. Of course, we could write out the substitution if we need to, but this one's relatively simple because if we did, u equals 3x minus 2, then du would be 3 dx. So I just have to borrow 1/3. And so if you see that substitution, you don't have to write it out. You can just write the result. Whenever u equals some linear function, you can just skip writing that part out. So this will be 1/3 times, ln of, if I plug in 6, what is that, 16? Yeah, 16 minus ln of, plug in 1, you'll get 1. Yeah, and ln of 1 is, of course, 0. So I get 1/3 ln of 16. If I want, I can manipulate this a little bit and say, oh, well, 16 is 4 squared. And I can, when you have a logarithm of an exponential expression, the exponent, the 2 in this case, can move out front. So if I want 2/3 ln of 4, if I think that makes it look simpler, but perhaps not a big difference. And since this is an application problem, I want a decimal. So 2/3 times ln of 4, and I get 0.924. And this is, of course, in grams. Okay, so now I want to look at doing circular objects. So if I make a circle, and I'll draw a big plus sign, because I do want to be able to point out the center of the object. So I make a big plus sign, and I should be able to get the circle to snap to. Yeah, there we go. It's in the center. So what if I had a circular object, and the density was given as a function of distance from the center, okay? So let's say rho of x equals the density function, density as a function from, function of distance from the center. Okay, which I kind of already have written here, but that's okay. So this point, say I draw another circle, right? And I go and I snap that to the center of this one. This position right here, oops, it doesn't want to let me do it. Okay, this position here, this spot, and this spot here, the material will have the same density. So all along here, we'll have uniform density on this circle. Oh, okay, uniform density along a circle. We're going to put together some ideas that we've used before to do something with this. So what I'm going to do is I'm going to duplicate this circle, make it a little bit bigger, tack it on there, and center it. So now I have a ring that has almost uniform density. It has thickness to it. So if I zoom in, this spot right here does not have the same density as this spot right here, but I could say, you know what, let's just pick a spot in the middle somewhere and use that to represent the density of the entire thing. So I could say, well, let's do this. I could say, let's label this spot right here. Let's call this xi. It's the distance, it's some distance from the center that marks the outer edge. And this guy right here, it's kind of hard to see. This guy right here, xi minus 1, okay? So this is the distance on that x-axis. So I'm going to mark here's xi, well, here's xi star, okay? And we're going to use that to mark the density. The density, we'll say, of the entire ring, the density is about rho of xi star. We'll use it as a representative, right? So now I have a ring, and we've chosen a representative density. What I'm going to do is I'm going to pop that out of, oops, wrong tool there. I'm going to pop that out. I'm going to copy this and erase the other parts, and just keep that ring for which we've chosen a density. So I'm going to duplicate that, bring it down here, running into my next example there. And I'm going to erase the bits that we don't need right now. So I'm going to get rid of all this as well. Okay, and you know what? We'll get rid of this as well. I guess I don't really need it. And if I try to get rid of this, I'm probably going to end up erasing the whole thing. Yep. There we go. Okay. So what we're going to do is, I'm going to take this guy up here, and we're going to cut it like right here and unwrap it. Okay. So I'm going to turn this into the following. It's like I'm cutting at two places, or cutting at one place and then bending it slightly to get it to come apart, which is visually a little bit hard, but there, I'm cutting it, and I'm going to unfurl it and unwrap it, okay? So then I'm going to have a thin rod of uniform density on that entire rod. Let's pretend that this is the right length, right? The length of this guy, well, that's going to equal 2 pi r, right? Whatever the radius is. Well, that radius is going to be the distance along here. Let's call that xi. So this is going to be 2 pi xi, okay? And the thickness, this is delta x, okay? That's the distance from xi to xi minus 1, okay? Now, something I forgot to mention earlier up here is that the density, since this is a thin plate, it's two-dimensional. This is going to be our circular object. I haven't called it a thin plate yet. It's a circular object, which we'll call a thin plate usually. This is not in grams per centimeter. This is in grams per centimeter squared, or whatever units you want. But I'll say for this example, this illustration, grams per centimeter squared. Okay, so now the area of this guy, well, it's going to equal the length times the height of the rectangle, right? This is 2 pi xi delta x. That's the area, and this is an area. This one's in centimeters, and this one's in centimeters. Okay, so this is in centimeters squared. It's a pretty bad M right there. Let's change the size on the stylus. Okay, so this area is in centimeters squared. 2 pi xi delta x. That's the area of this ring. Okay. So to find the mass of just that section, well, that's just going to be the area times the density. Because remember, the density is in terms of grams per centimeter squared per area unit. So the mass, I guess I'll call that mi, is going to be 2 pi xi delta x times rho of xi star. Okay? So that means that the mass of the whole plate, or at least our estimate of the mass, I'll call it EM, estimate of the mass, well, this is going to be the sum as I goes from 1 to n of, and I'm going to switch the order of these two guys. I'm going to put delta x at the end, only because that's usually what we do, not because it needs to be done. So this is going to be 2 pi xi times rho of xi star times delta x. And notice I have centimeters times grams per centimeter squared times centimeters. So I get a bunch of cancellation. I'm adding up grams. Okay, I'm adding up mass. Okay, so as per usual, the mass itself, the exact mass, well, this will be the limit as n goes to infinity of the sum as I goes from 1 to n of 2 pi xi times rho of xi star delta x, which of course, I'm basically out of room here. This is the integral, well, from where to where? If we go back to our original circle, I need to integrate in the x direction. So this is basically you're integrating through the radius of the original object. So I'll say from 0 to r for radius. And you know what? And if you had a gap in the middle, like if you had a big blank spot here, then I guess you would like if you had a disk with a hole in it, then you could integrate from little radius to big radius. But let's just say for a disk. So let's say from 0 to r of, well, 2 pi x rho x dx. And when you're building your integral, I want you to think about, oh, this is a distance, right? This is centimeters. This is a density. This is grams per centimeter squared. And this is a distance. This is also in centimeters. Okay, so I'll write this larger here so when we come across it later, it'll be a little bit more prominent. So the mass for the two-dimensional object is given is integral from 0 to r, whatever the radius of the object is, 2 pi x rho of x dx. And here's a shot of that whole progression. We described our problem, right? I picked a ring, not in the center, not at the edge, somewhere in between, to represent the whole thing, right? A representative ring. We talked about getting a representative density. We cut the ring out, and then we split it at one position and stretched it out to make a rod of uniform density that we've chosen a representative. And then we apply what we talked about before about, oh, you're just multiplying the density with the well, it was before length. Now it's area because we have a thickness to our ring. But yeah, and then we build the integral. Okay, so let's do an example where we find the mass of a disk with a radius r equals 2 centimeters with density function delta of x equals 2x plus 1 grams per centimeter squared. This time we'll use delta instead of rho. It's not an important difference, but I just wanted to do both at some point because some books use one versus other books use the other. So, yeah, I'm going to do the integral from 0 to 2, because the radius is 2, of 2 pi x times the density function dx. Okay, I'm essentially just using as a formula, I want the circumference of that representative ring times the density function times dx. These two together make the area of that ring, and the area of the ring times the density function gives you the measurement in grams, the mass in grams. Okay. Okay, so this will be, it's a pretty easy integral, but you know what? I should probably move that 2 pi outside. Why not? Let's do that. So I'm going to have 2x squared plus x dx. So this equals 2 pi times 2x cubed over 3 plus x squared over 2. Evaluate at 0 and at 2. Kind of running out of room here. So this equals 2 pi times, well, this will be 16 over 3 plus 2 minus 0. So 22 thirds, so 44 pi over 3 is the resulting mass. And as per usual with these application problems, we might want a decimal number for this, decimal approximation. So 46.077 grams. Okay, let's do another example, find the mass of a disk with a variable density. So let's say the radius again is, well, 2 meters this time. So the radius is 2 meters with density function delta x equals cosine x squared plus 1 kilograms per meter cubed. So different units. I'm just making sure that I'm matching the units in my density function with the units in the radius that I'm given. Like if a problem were to give you centimeters for one and meters for the other, you would need to convert to make both of them centimeters or both of them meters. Probably later we'll be doing meters instead of centimeters because we'll be doing things like newtons and joules, and we'll need to make sure we're sticking to SI units. Okay, so I'll just set up as we did in the previous example, the integral from 0 to 2, well, of 2 pi x times the density function plus 1 dx. Okay, and again, remember that not that it's important, not that it's essential for this example, but we want to keep this in mind for future examples when we're building new integrals. This is in meters, the highlighted part. This is in kilograms per meter squared, and then this is in meters. So I have meters times kilograms per meter squared times meters. So all the meters cancel out, and I get kilograms. Okay, so I'll move the 2 pi out front, and I'll distribute that x. And it might not be obvious immediately what to do with this one, but maybe it's not confusing or anything. There's 2 ways to go from here that I see. We're going to need to do a substitution. Notice that the derivative of x squared is proportional to x, right? So either you can see what to do. Oh, well, we're going to need to borrow a 2. And you probably could get away with not writing out the u substitution. Or I shouldn't call it u substitution, but without writing the substitution. I'm going to go ahead and write it out to make sure this is as clear as possible. So I'm going to say that v equals x squared. So dv equals dx. And, sorry, 2x dx. And I'm going to need to split this integrand into 2 because this guy doesn't require substitution at all. I don't want to convert this into v. That would make things really complicated, so I don't want to do that. So I'm going to have 2 pi times the integral from 0 to 2 of x cosine x squared dx plus the integral from 0 to 2 of x dx. Okay. And then I'm going to manipulate this guy a little bit, and I think I'll leave this one until I'm ready to do the antiderivative in the first integral, and then we'll do both antiderivatives at the same time, rather than having each integral at a different phase. That's not important. It's not important to do them like that, but that's what I'm choosing to do here. So I'm going to need to borrow a 2, right? So what I'm going to do is I'm going to go ahead and distribute this 2. So I'll do pi times, I probably should have done this in the first place, but that's fine. Okay. So now I need to move this 2 inside. So I'll have pi times integral from 0 to 2 of cosine x squared 2x dx plus 2 times the integral from 0 to 2x dx. So this equals pi times, well, this will be the integral. V is x squared from 0 to 4 cosine of v dv plus 2 integral from 0 to 2x dx. Again, I'm waiting until I can do both antiderivatives at the same time. I'm probably running out of room here. Yeah, well, okay, I got some room. So pi times sine of v, evaluate at 0 and at 4, plus, will that be x squared, 2 times x squared over 2, so that ends up not mattering from 0 to 2. Go ahead and cancel these. Okay. So I will get pi times sine of 4 minus sine of 0 plus 4 minus 0. So I get pi times sine of 4, which obviously is not a nice clean number, plus 4. And then this is in kilograms, right? So that's my exact answer, but of course, in an application problem, we will usually want a decimal approximation. And I need to make sure that my, because I'm using a calculator here, obviously, that I'm in radian mode when I do this, because if I use degrees, I will definitely not get the right result. So I get about 10.189. 10.189 kilograms. All right. So the next few examples will be about work done by a force. Work in a physics sense is defined as a force applied over a distance. So when you lift something heavy, you move something heavy on the ground, something like that. In the standard SI units, the standard unit of force is a Newton. So a Newton, or in other words, 1 Newton, is 1 kilogram meter per second squared. Basically, this is equivalent to, if you think about F equals ma, right? Acceleration is meters per second squared. Kilograms would be mass, so that's basically what we're basing this upon. Kilograms is mass, acceleration is meters per second squared. Okay, so 1 Newton is 1 kilogram meter per second squared. 1 joule would be moving, applying a force of 1 Newton over a distance of 1 meter. So this would be 1 Newton rather, times 1 meter. So in other words, 1 kilogram meters squared per second squared. And you might look at that and go, oh, I mean, there's area involved? No, there's no area. Not really. The units don't break down like that. But when we're building our integrals to talk about work, we're going to want to make sure that our units are in joules. We have kilogram meters squared per second squared built into the integral, and that way we know we're calculating work. In non-SI, usually what we would often use in the US, obviously in science, we usually use SI anyway, but we should talk about the non-SI units as well. So foot-pounds force is something you may never have heard about. This is the measurement of work in non-SI. So probably what I should do is start with pounds force, okay? Pounds force you may never have heard of. I weighed myself this morning, and I weighed 192 pounds. I'm working on it. Now someone tells you you weigh 192 pounds, you go, oh, okay, that seems healthy. But I'll tell you, no one weighs 192 pounds. No adult human, certainly. Maybe I guess a newborn might weigh that much, and here's the reason. Would you say that you weigh something in kilograms? Do you weigh in kilograms? No, your mass is in kilograms. You weigh in newtons, because newtons is the unit for force. So in the non-SI, American system of units, this is false. I do not weigh 192 pounds. This is pounds mass. My mass is 192 pounds. My weight, at sea level, for example, I'm not at sea level, so my weight will actually be slightly less than this. But let's say I go to the ocean, right? My weight at sea level is going to be 192 pounds mass times 32.174049 feet squared. Sorry, feet per second squared. That's because this is a unit of mass and this is an acceleration. Mass times acceleration. That's force, which is what a weight is, right? So my weight in pounds force is going to be, let me grab a calculator, 6,177 point, I'll round it to one place, 0.4 pounds force, and the usual symbol is LBF. This is my real weight, okay? Which is not as impressive. Well, I mean, depending on, your the sport you're in, right? That might be really advantageous in certain conditions, right? But this is just not what I weigh. This is what I weigh. And this is something we're going to have to pay attention to when we're building integrals using units. Well, make sure that you're talking about is this pounds force or pounds mass? So, what is foot-pounds force? I just realized this is a header in force, and this is a header in work. So, here's what we're going to do. We're going to fix that right here at the end. Joules should be the header. Sorry about that. So, what do we have to add to bring this over here? What's the analog? Right? I just wanted to bring this up first. What is the analog to that? Well, one pounds force, which I believe is, or sorry, foot pounds force. 1 foot-pounds force is foot pounds force, right? This is the work done by moving 1 pounds force through 1 foot. 1 pounds force times 1 foot. Why does the order get switched? I don't know. That's just the way it's written. So this is going to be, well, pounds force is, as we can tell from up here, pounds mass times feet per second squared. So this is going to be pounds force, that's 1 foot times pounds per second squared. In fact, you know what? I'm not going to switch the order there. Sorry. 1 pounds mass times feet per second squared times 1 foot. So this is going to be 1 pounds mass feet squared per second squared. So over here we have a mass. We have a mass. We have a unit of distance squared. We have distance squared per second squared per second squared. Okay, so the SI unit for work is joules. The most common non-SI unit for work is foot-pounds force. Okay, so another example, a 30-foot rope with density 0.5 pounds per foot dangles from the roof of a tall building. How much work is done in lifting the rope to the top of the building? So notice that this is pounds mass, not pounds force, so we're going to have to make sure we adjust for that. So I'm going to talk about first lifting just a simple object, and then we'll talk about something like a rope. So let's say we have like, I don't know, let's say we have like a 20-pound rock, right? We want to lift it, I don't know, 5 feet. Something relatively simple, right? You know how to lift a 20-pound object 5 feet, probably. So what I want to do is think about, I'm going to be doing, work equals force times distance, and the distance is 5 feet. Well, what's the force involved? Well, this is pounds mass, not pounds force. You're opposing gravity every step of the way as you lift the rock for 5 feet, right? Now, of course, in a technical sense, when you lift an object, its acceleration due to gravity changes, but let's not worry too much about that, okay? So the constant for acceleration due to gravity in the standard, the American system, the non-SI system, is Gn. I forget what the n is for, but this is basically the gravitational constant. This is 32.174049 feet per second squared, which we're not always going to need that many decimal places, but we might as well, at least most of the time. So the force we're going to be opposing is going to be 20 pounds, okay? 20 pounds mass times 32.174049 feet per second squared. And this will give me 643.48098. This will give me pounds force, okay? This is pounds feet per second squared, okay? Pounds times feet over seconds squared. And I may want to refer to this differently. We'll see how this goes, because later on I want to make sure I'm dealing with work, and work is pounds mass times feet squared per second squared. We may have to change this back into its constituent parts, which would be these guys, but we'll see. So that's the force I'm opposing. So the work is going to be 643.48 098 pounds force times 5 feet. Okay, so that times 5, that number I had times 5, gives me 3217 times 4049 pounds force times feet, which is often referred to as foot pounds force, hyphenated, foot pounds force, which is the standard American measurement of work. So that's moving a single object a fixed amount of distance, okay? Now, what if we were moving a rope? Because the rope it is a single object, but if you think about it, dangling from the top of a building, then the bit of rope at the top already or near the top doesn't have to move as far. So this is the formula when moving a fixed distance. Okay, what if you have a variable distance in a fixed fixed force, right? So you might say, well, my work is going to be the integral from wherever to wherever of some force, which could be a function, maybe, times some distance, which could be a function, maybe. There's no dx written here because it's not immediately apparent where does the differential come from. It has to come from either the force or the distance. Okay. So let's draw a diagram to represent this. Let's say, so I'm going to have something for the rope to dangle from, and I'm going to say that the rope I'll represent. Again, this bit up here doesn't have to travel as far as this bit down here. This bit has to move all the way up here, the 30 feet. So what I'm going to do is take a small representative section, and I'm going to say that it is X feet from the top. Okay, so this section is 0 feet from the top, or 1 foot, or whatever. And then this section in here is 30 feet or 29 feet, however you want to call it, right? This section here, it's got height to it because it's dangling. But I'm going to say, you know what? It's just X. It's X feet from the top. And the length of that section, we're going to say is dx. Okay. Change the thickness of my stylus here. Dx is the thickness of that section, or the length rather, not the thickness. Thickness would be this way. How wide is the rope? But this is like the length of that little subsection. Okay. So what's going to happen is the force is going to be the differential part, because the force is based on, well, how much is it? How long is the piece? Like if you were to cut the rope into pieces and you have a short piece versus a long piece, well, the long piece weighs more. So there's more force needed in order to move it however much distance you want, because it weighs more, right? So when we go to build our differential, for the work, we're going to say, okay, dW, this is the differential of the work. This is going to be the work to move the one section. In order to work out what the differential of the work is, well, I need to know what's the force involved, what's the distance involved, right? So dF, the differential of the force, meaning the force for just that section, okay? This is going to be, well, dm times acceleration. The dm is the mass of that section, okay? So this is going to equal, well, 0.5 pounds mass per foot. That's the density of the rope, right? That's the mass density, times dx feet, okay? I have the mass density times the length. I get the mass. So this together makes the mass in pounds mass. When we do an example with SI units, this might be a little more straightforward, but we have to do some in non-SI units. So now I have to multiply by the acceleration due to gravity. So times 32.174. I'm going to round to 3 places. We don't need to keep 6 places all the time. And this is feet per second squared. Okay. So if I total all that up, I'm going to get, this is 16.082. And I can think about if I want these feet canceling with these feet or with these feet. It doesn't really matter. We're not going to need to keep track of, well, which foot canceled. That we don't have to worry about that. So this is going to be pounds mass times feet per second squared. Which is, if we want, 16.082 pounds force. Okay, we don't need to talk about pounds mass anymore if we don't want to. So that is the force due to gravity working on that section. Okay. So the work involved, dW, is going to be 16.082. Oh, I forgot the dx. Yeah, dx. Okay. That's relatively easy to fix. Hold on. Okay. dx is kind of important here. So 6.082 dx pounds force times, well, what's the distance? Well, this section has to go up x feet. That's how far it was from the top. Times x feet. Okay? So this is going to equal 16.082. Changing the order a little bit, x dx, because we usually put dx at the end. This is pounds force times feet, or if we want, the more standard way to refer to it is foot-pounds force. So this is hyphenated, not a product. Foot-pounds force. Okay, so this is the work required to move just that little section. So what if we want to do all of the little sections? Well, the length of the rope was 30 feet. So this section, or, well, the last little incremental bit has to move 30 feet. The section that's basically already at the top has to move 0 feet. So that's going to be the integral from 0 to 30. So the work involved is going to be the integral from 0 to 30, 16.082x dx, and I won't bother with the units in the integral. Okay, so this equals, well, that's going to be a 8.041x squared. 30, not 3. Sorry about that. 30. Evaluate at 0 and at 30. Okay, so this will be 8.041 times 30 squared minus 0, and we get that this is 7236.9 foot-pounds force. Here we go. That is the way to build the integral and calculate the work needed to lift the rope that's 30 feet long and dangling all of it to the top of the building. Okay, so let's say we are wanting to calculate the work required to compress a spring. So if it takes 20 newtons to compress a particular spring by 0.02 meters, how much work does that require? So Hooke's spring law describes the force required to compress a spring for small compressions. For large compressions, this is not very accurate. So F equals Kx, meaning that the force required is proportional to the displacement. How much are you compressing the spring? Small compressions, small force. So basically, if we wanted to compress down to 0.02 meters, to at that point hold it is 20 newtons to hold it at that point. So 20 newtons would be a number we can plug in for F. So then K times 0.02 meters, hey, that would be matching the spring law. So I could divide by 0.02 meters and get 1,000 kilograms per second squared. That's the constant for that particular spring, and other compressions would follow the same equation. So if I wanted to compress to 0.03 meters, well, that would be 30 newtons would be required to do that compression. So that's basically how we determine for a given a given displacement goal to hold it there, how much force is required to hold it. Now, if you want to compress a spring from equilibrium down to some compression, you have to go through all those different levels of compression to get to the one that you want. So if we have a graph like this to represent a spring, let's say at the right end, right here, this is where the spring is fixed or attached to something. It's not going to move, okay? And then, so over here at the other end, this is where I'm going to push to compress the spring. We could do pulling, stretching the string, but let's do pushing only for this example. So let's say here I am at equilibrium, I have zero compression. That's why I have it at the origin. Let's say I wanted to compress it down to here. Let's say there's C, okay? And I'm gonna talk about this in stages so we can relate it to an integral. So I'm first gonna compress up to this point. I'll push on this until I get to over to here, and of course all of these will move down a little bit. The entire spring compresses, right? A little bit for each piece. Then I'll compress to there, then to there, then to there, and there, and there, and there, and there, and there. Okay? Now let's say I wanted to talk about what is the force required to hold this level of compression? Well, that would be, well, how far is it? That would be, the displacement would be, well, delta x, I guess, right? We'd be going through one of these incremental changes. Be delta x would be the distance, so f of delta x, that's how much it would cost to hold it there, right? And then holding here would be f of 2 delta x, f of 3 delta x, and so forth. But what if I wanted to calculate the work to get to this position? Okay, well, then what I could do is say, well, let me pick a representative. Let's say that this is x1 and this is x2 and this is x3. Okay. And in fact, I should probably change my stylus to be smaller. Let's say that right here I've got x1 star, and I'm going to say that's representative of the force required for this entire interval, because I got to pick a number to work with, right? So that would mean that the force, the force is going to be, well, let's just call it f of x1 star, okay? So that would mean that the work to do that would be, well, the force over the distance. What's the distance again? Well, delta x. So that would be f of x1 star times delta x. That would be the work to do that compression, okay? What about to go from here to there, to compress the spring a little bit further? Well, I could pick a representative and say this is x2 star. Say, oh, okay, well, the force required to do that That's going to be F of x2 star. So then the work required to complete that compression will be F of x2 star delta x. And you can probably kind of see where this is going. We're building a Riemann sum, essentially. We have a function evaluated at representative times an incremental change in the coordinate. So why don't we skip over to here and say, well, let's just say that this is x. Our representative is x. Our distance is dx. So the force required at that position will be, well, whatever f of x is. So the incremental work to complete that compression will be f of x, the force required, times dx, the distance through which we'll be moving. Okay, and of course, this is in newtons and this is in meters, so we're dealing with joules, right? So then to find the total work, this would be the integral from 0 to c, the compression spot I wanted to go to, of f of x dx. And there you go. That's how you calculate the work to compress a spring once you have the spring constant. So for this one, for this example, well, there's my spring constant. So that means that the function that describes the force, F equals 1000x. Right, it's this guy, 1000 times x. So the work required to do that compression will be the integral from 0 to 0.02, because that's how far I want the compression to go, of 1000 x dx. All right, this is the force required at an incremental position, and this is the distance through which we're going to do that increment, and force times distance will give you work. So this will be, I guess, 500 x squared. I'm going to run out of room here. Evaluated at 0 and 0.02. So this will be 500 times 0.02 squared minus 0. Let me get the calculator out. Probably I could do that without a calculator on, but let's just do this. It'll be faster. Unless I press the wrong button at the beginning and have to start over, of course. So, yeah, it probably would have been not too bad. This is 0.2 joules. Okay, so that is the work required. Not a whole lot to compress. 2 centimeters is not very much, so you're pressing on a spring and you can press it just a little bit. So in this example, we're going to look at pumping water out of a tank. So let's say a cylindrical tank with height and diameter of 2 meters each is filled halfway with water, while standing upright, of course, as per the diagram. How much work is done by pumping the water to the top in order to drain the tank? We don't want to just drain out the bottom. We don't want to put a hole in the tank and let it drain. We want to reuse the tank. So we're going to put some sort of straw-like device in there and then pump the water out, right? And maybe it drains off into something else. So this is actually, turns out, a lot like the rope problem. So I'm going to copy part of this because I want to pick a representative slice of the water. Okay, so let's say we have a small cylindrical slab of water. And let's say that this, this line here, there's a couple of ways to do this, but I think this will work fine. Let's say this line here is an x-axis, okay? Try to line it up real nice and neat, okay? So here is where x equals 0, and here x equals 2. And of course, if the water's half full, x equals 1 right there. So I want to say that the slab has height x and thickness dx. Hopefully that seems reminiscent of what we did with the rope problem. So since I want to know how much work does it take, I want to say, well, work is force applied over a distance. So what is the weight of the water? And then I can multiply that by the distance, x, perhaps. We'll check on that in a few minutes. And then, hey, that's the work for that section of water. And then I can integrate to get all the slabs of water, okay? So one thing we're going to need to do is to talk about, the order in which we do this is optional, but what I want to talk about is how we're going to have to do a conversion, because we are just told that there's water. Okay, well, how much water, right? We're going to need that in newtons. How much force is that? So conveniently for the metric system, 1 kilogram of water, um, uh, I'm sorry, is 1 liter. So 1 liter of water is 1 kilogram, right? So there's 1 kilogram per liter. And it turns out, if you do some unit conversion, that turns out to be 9,800 newtons per cubic meter. Okay, we're going to need that because all of our measurements are given in meters. So we're going to need to be able to convert from cubic meters into newtons, and because newtons, that's the force that we're working against when we lift the water. So this slab here is going to have a radius, right? It's going to have a radius. I guess the center is right there. The radius is going to be, well, the base of the tank has a radius, diameter of 2 meters. So the radius is 1 meter, right? So that means that the area of the base there is going to be, well, pi r squared would be pi, right? So the volume, and I'm going to call this dV for now, it's the incremental volume, is going to be, well, that's going to be the area times the height, and the height of that slab is dx, it's the thickness. So this is pi dx is the thickness, and this is in cubic meters, okay? So I want to turn this into mass, all right? I'm sorry, not mass, but into newtons, into the force we're opposing. So the incremental force that we're opposing, dF, this is going to be, with this conversion here, we're going to convert the meters cubed into newtons. So 9,800 times pi dx will give us the weight in newtons. So 9,800 pi dx, and this is in newtons. So what about the work? Well, remember, work is going to be force times distance. So it's definitely this dF, 9,800 pi dx. And I'm going to drop the units for now, I think. I won't put them here. I'll put them at the end only. Times, well, what's the distance? How far up does that have to move? Because x is measured from the bottom, right? So when x is very small, we'll have a slab at the bottom of the water. As x gets closer to 1, we'll have a slab at the top of the water, right? The last slab, if you want, will be the top, depending on how you want to count things. So the distance is from the top of the tank. Let me change the highlighter here. The distance is from the top of the tank down to the slab, okay? Or in other words, change that again. From the top of the tank down to the slab. Well, that's going to be 1 unit plus whatever remains out of x, because x is measured from the bottom. So really, I could say that the distance is 2 units minus whatever x is, and that will be the remainder right here from the slab up to the top. So 2 minus x is the distance. 2 minus x, and this will be in joules, okay? So then we can integrate to get the total work. Integral from 0 to 1, because that's from the bottom of the water to the top of the water, of 9,800 pi dx times 2 minus x, okay? Which, of course, I can move the 9,800 pi out front and switch the order of the 2 minus x and the dx so it's a little bit more recognizable. We usually write dx at the end when we're doing an antiderivative, and when we're building an integral, of course. So this will be 9,800 pi times 2x minus x squared over 2, evaluate at 0 and at 1. So this will be 9,800 pi times, well, 2 minus 1/2 minus 0. So 3/2. So what is that? 14.7, I guess. 9,800 times 1.5. Yeah, 14,700. 14,700 pi joules is our result. And I didn't write joules every time. I mean, I guess I could have gone in all these and put a J at the end, but we don't really need to do that. And as usual, we might want a decimal approximation to say, well, yeah, but how much is that? If we wanted to specify, you wouldn't say you were going to check a generator to make sure you had that capacity, or a battery to make sure you had that capacity. It's not listed in terms of pi units, right? So 46 181.412 joules is the energy required to do that. So we could, if we wanted to, round that to 46 kilojoules if we had a reason to round it. So, a conical tank with height 8 meters and diameter 6 meters is filled halfway with water. The tank is upright and inverted. How much work is done by pumping the water to the top in order to drain the tank? So I've got a diagram here, and I've drawn out a representative slab of water. This is a lot like the previous example. I'm going to mark down the, ballpark the center of the top of the slab, and mark the radius of the slab. And note that, the top of the slab is X units from the bottom, marked 0. Okay. Now, since we have a cone and not a cylinder, we do have to do a little bit more work because the volume calculation is a little bit harder. Basically, we're going to have to use some similar triangles. So the problem says that the diameter of the top of the tank is 6 meters. So this distance here is 3 meters, right? The radius at the top. So basically, we have a big triangle here and a little triangle here that are similar triangles. So basically, 3 over 8 is r over x, essentially. If we wanted, we could probably redraw this. We could say that, I'll draw it a little bit smaller, but basically the same thing. So this is the larger triangle, 3 to 8, right? And then the smaller triangle is something like right here. In fact, I'll do it in red. This is r, and this is x. So that means that 3 over 8 equals r over x. Okay, of course, x is the inside, and 8 is the entirety of the outside. So that means that 3 over 8 x equals r. So the radius of the top of the slab is 3/8 of whatever x is. Okay, so then we can repeat the calculation that we made in the previous example, but knowing, well, the radius is not, just some constant number. I guess it was 1 in that case, 1 meter. We're going to have to say, oh, well, it's this formula. It's this function of x. So the area of the top of the slab, that's going to be pi r squared, of course, but of course r is 3/8 x, so pi times 3 over 8 x squared. So that works out to 9 pi over 8 times x. Oh, not 8, sorry, 64. 9 pi over 64 times x, okay? So that means that the volume dV of that slab will be, oh, you know what? We didn't label that. Pause the video and think about how thick is the slab. If the slab is at height level x, how thick is the slab? So the thickness of the slab is dx. I can label it there, or I can label it here. It's an incremental amount in the x direction. So over here, the dV will be, well, that area times dx, the thickness. That will give you the volume of that cylindrical slab of water. So this will be 9 pi over 64 x dx, okay? That's the volume. Now we need to look at the work involved, okay? The force involved, rather. The force to move that volume of water, or at least the force due to gravity on it, because we have to oppose that to move it. So we're going to do the same thing we did with the previous example with water being 9,800 newtons per meter cubed. So the force acting on that water due to gravity will be 9,800 times this volume. So 9,800 times 9 pi over 64 x dx. Okay. Now I can look at, okay, what is the oh, x squared, I'm sorry. My mistake. X squared, x squared, x squared. Sorry about that. Okay, so that's the force involved. So what is the work involved? Because remember, the work involved to oppose, the work is basically a force applied over a distance. Well, what distance is that slab going to move? And so basically, the slab is at height x, and it needs to move all the way up to the top of the, yeah, I can mark it there. If the slab is at height x, in fact, I'll do it like this. The slab is at height x, and it needs to move all the way to the top of the tank, right? Well, it's going to have to move from x up to 8, so 8 minus x. So the work involved is going to be 9,800 times 9 pi over 64 x squared dx times 8 minus x. And I can put joules here if I want. I don't have to necessarily, but might as well. That's okay. That's the incremental amount of joules. That's the joules required to move that slab of water. So if I want to find, well, what's the work to move all the water? Well, then I just need to integrate. Where am I integrating from? Well, the water goes from 0 up to 4. So that is the integral that I'll be doing, 0 to 4. So this will, W equals the integral from 0 to 4. I guess I can go ahead and multiply 9,800 with 9, I guess, to get, what is that? 5620, I think. Let's see, 9,800 times 9, 8820. Yeah, not sure why I thought 56, 8, 90, 8820, 88,200, sorry. Okay, so 88,200 pi over 64, which those are, there's even numbers in the top and bottom of that fraction, so obviously we're going to be able to reduce at some point. X squared times 8 minus x dx. We usually put dx at the end. If I had left this order, that wouldn't be incorrect. Just, at some point, we're going to need to distribute the x squared. So it makes sense to do it here. I could probably reduce. What's 88,200 divided by, oh, that's 11,025. Okay. So this equals, because 88 divided by 8 is 11, 200 divided by 8 is 25. So when I move these guys out in front of the integral, I'm going to have 11,025 pi over 8, okay, times the integral from 0 to 4 of 8x squared minus x cubed dx. And then this is a relatively simple integrand to deal with. So 11,025 pi over 8 times 8x cubed over 3 minus x to the 4th over 4, evaluated at 0 and at 4. So 11,025 pi over 8 times, well, it's going to be 8 times 64 over 3 minus, well, 64, 4 to the 4th over 4 is 4 cubed, so 64. Okay, minus 0, of course. And I notice I've got an 8 here and an 8 here. This is divisible by 8, so I'm going to go ahead and reduce. And cancel that, cancel that. This reduces to 8, right? So I'm going to have 11,025 pi times 64 over 3 minus 24 over 3. Okay, so that's 40 over 3. What is 11,025 times 40? I get 441,000 over 3, which is divisible, so, evenly. So this equals 147,000 pi, which is a pretty big number, and in joules, right? And usually we'll want a decimal approximation for application problems. So I get about 461,000 814.12. Yeah, joules. And if we want, we can write that as approximately 461.81 kilojoules if we want. Or if you'd really like to, you could say, oh, well, that's about 0.461 megajoules. If you wanted to do that, you could. Anyway, so there's a lot of steps there, but a lot of that was, the integral, working out the integral after we worked out the integrand, and then also, the similar triangle step. So I noticed looking at this afterward that I did not round this correctly. So if I want to round there, then I should not have a 1, I should have a 2 in that position. And so that's fine if that's what I want to do, if that's how I want to round. Okay, so the next application is what's called hydrostatic forces, basically the force on an object due to being submerged in a fluid, specifically water in this case. So let's say we're at some sort of pool or reservoir, something that holds water, and there's a wall, a vertical wall. It turns out that vertical doesn't really matter, that the force, these kinds of forces apply in all directions, so the orientation doesn't matter. Let's say there's some sort of grate or plate at the bottom of the pool, okay? And let's say that it's, I don't know, let's say it's 4 meters wide and 3 meters tall. Okay, the 3 is already marked out here. Let's say that in total, the water is 10 meters deep. So we could ask, what is the force that applies to that plate at that depth? Well, the basic formula is that the force equals the depth at which the object is times the weight density of the fluid, and we'll probably be using water, weight hyphen density, okay, times the area of the object, okay? Now, if we want to do something really simplistic, we could say, oh, well, this is 12 meters, right? It's at the bottom, so what's the depth exactly? Is it 7? Is it 10? So what we need to do is pick a representative slice. So I'll say, I'll make a rectangle, hopefully. Yeah, the auto rectangle tool is working with me. Let's pick a little bit thinner. Let's say we're going to pick a representative slice, okay? And it is at height x. In fact, let's do this. Change that thickness as well. It's at height x. And the thickness is dx. So we ask, what is the depth? We can say, well, that slice is at depth 10 minus x, right? This, from 10 down to the bottom would be 10 meters, right? But if we stop x units short, then that would be 10 minus x units. So the depth would be 10 minus x for each slice. So the weight density, well, that's going to be 9,800 newtons per cubic meter. That, since we're using water, we'll just go with that. Now, what's the area? Well, the area for each slice, right? I change the size of my marker here. This guy, this area, well, it's going to be 4 times dx, because that is the area of that rectangle. It's 4 meters wide, dx units tall. So the incremental force, change my stylus up here. The incremental force, dF, well, let's say dA, let's start with that, is 4 dx. In other problems, this will be the hard part often, but for this one, it's pretty straightforward. So dA equals 4x. So dF, the force on just that slab, is the depth, which is 10 minus x, times the weight density, which is 9,800, times the area, which is 4 dx. And as we've done it a few times, I want you to think about this depth, oh, let me change the marker size. This depth is in meters. This weight density is in newtons per meter cubed, right? And this area is in meters squared. Meters times newtons per meter cubed times meters squared. So these meters will cancel with that one, and we're left with newtons. So we are calculating a force. Whenever you're setting up these integrals, checking the units is a good way to make sure you haven't missed anything. But you do have to be aware of, well, what units am I using? What is 9800? So you have to know the units, but then they help you check that you're not missing anything. So the total force applied to that plate, well, this is going to be the integral from 0 to 3, because that's the total height of the plate, of, well, 9800 times 4, what is that going to be? I will just be, take a shortcut here. I have a calculator handy. So that's 3920, or 39.2 rather. So 39,200 times 10 minus x dx. So I could write this as 39.2 times the integral from 0 to 3 of 10 minus x dx, which then turns into a pretty easy integral. So 39.2 times 10x minus x squared over 2, evaluated from 0 to 3. So this would be 39.2 times 30 minus 9 over 2 minus 0. So 60 over 2 is a 51 over 2. Pretty sure that's right. 39.2, that's divisible by 2, so is that 19.6 times 51? What is that? And I get 99,990, 99,960. And that is in newtons, because that is a force that we're calculating. I almost wrote joules. No, that's force. So there's an example of a hydrostatic force. Now, is it just 3 times 4 times, well, what would the depth be? The average depth? Would it be, I don't know, 8.5? Is it just 8.5 as in the depth times 9,800 times, 12? Right? That's the area. Is that correct? Well, what's 8.5 times 9,800 times 12? And indeed, we do get 10 off of that. So I might have a factor of 10 somewhere. Yeah, because I get this, which is 10 times too much. So we may be missing a 10 here. At the end of this, I'll point that out. I'll go back and check, and if I find a missing 0, which, that's a possibility, I will point that out if that's the case. Yeah, so basically, I did make a mistake. When I typed this in the calculator, I typed this number in wrong, so I'm missing a 0 down here. So this is actually that, okay? So for this example, I did have to think about 8.5 being the midpoint, the halfway on that plate. So if you just have a rectangular plate at the bottom of a pool, then then you don't need all of this. So next we'll do an example where we actually do need this calculation. So let's say we have a triangular trough with length 5 meters, whose ends are right isosceles triangles with hypotenuses of 1 meter and is full of water. Yeah, I read it differently, but the way it's worded is probably grammatical. Anyway, what is the force exerted on one end? Okay, so this is going to be a lot like the previous example, except that we don't just have a rectangular plate. It's the little slabs, or the little areas are going to have variable area. So the 5 meter length doesn't really affect anything. That doesn't matter. All that matters is depth when you're talking about pressure through hydrostatic forces. So the 5 meters, whatever, we don't care about that. The 1 meter, we do. That means that in the x direction, this is 1/2 of 1 meter, 0.5 here, and negative 0.5 here. Now this is a right isosceles triangle, right? It says so right there. So that means I know that this right here is a right angle, okay? And in fact, I'm going to mark it at the other end just because I don't want to clutter the graph too much, okay? Because we're going to have to draw some stuff here in the middle. I don't want to clutter it. 1, 1, root 2. So since the length is actually 1, and this is just a proportion, I'm going to divide by root 2 in each place to get the actual lengths. So this segment right here, that length is 1 over root 2. Okay, likewise, this one is 1 over root 2. Okay, that may become important. Also, this is 45 degrees, or if we want pi over 4, and this is also 45 degrees. So that may become important. That also means that this right here is 45 degrees. Again, that may become important because what that tells me is if this right here is 0.5 meters and this is a 45 degree angle, then this right here is also 0.5 meters. So I know the depth of the water now, 0.5 meters. Okay, so I'll just mark that right here, 0.5. That's a y coordinate, right? In fact, in this case, we're going to be integrating with respect to y because y is the depth variable. So I'm going to pick a representative section to start working because we need to find out what is the area beneath the water so we can work out what is the force. So I'll pick red and I'll try to mark out a rectangle. Maybe the rectangle tool will work with me. I want to make that, oops, nope. I want to make that a little thinner. Yeah, that'll work. Let's do that. So I'm going to put that over here and attach it like so, okay? So we're going to say that the depth of this guy, we're going to say is y units, and we're going to say that the thickness is dy units, okay? So then the question is, well, what's the area? So I need to know, as a function of y, what is the length? Because that length times dy, that's the area of that little section, that little rectangle. Now, because this angle here is 45 degrees, right? I know that the this line right here has a slope of 1, right? So I know that I could write that line as y equals x. So every point, in fact, let's do this. Y equals x represents, or is an equation that represents that line, right? So that means this point right here at height x is at horizontal coordinate, I'm sorry, at height y rather, is at horizontal coordinate x, right? So that means that the entire length of this thing, oops, need to change that to a smaller size. The entire length of this at height y will be twice whatever x is, right? This length here is 2 times x. It's the double of whatever this section is, right? This right here is half of the length of the rectangle. But since x equals y, this equals 2 times y. So the area equals, I guess I could call it dA, yeah? Well, I'll just call it A, that's fine. This is 2y times dy. That's the area of that section, okay? So the force, remember the force, let's change colors here. The force equals the depth times the weight density times the area, okay? So the depth, what is the depth? Well, the depth that this has to, from the top of the water, well, that's going to be from y up to wherever 0.5 is, the top of the trough. Well, so 0.5 minus y is the depth of that section. So 0.5 minus y times weight density, 9,800, as per usual for water, times the area, well, 2y dy. And again, we want to check that this is a distance, right? The depth is in meters. The 9,800 is newtons per meter cubed, and the area is meters squared. So that all works out to be in newtons, which we just should check for that. We're not leaving anything out. I'm probably going to run out of room here, so I'm going to bring this down here. In fact, I should call this dF, because it's the differential of F. It's the force for that slice. So that means that the force itself is actually the integral from 0 to 0.5, because that's from the bottom of the trough all the way to the top, okay? Because we're asked for the force on the entire end of the trough, not like if the trough were half full, then our numbers would be different, right? Because we wouldn't be going to 0.5, it'd be 0.25 because it's half full. Basically, since we're doing the end of the trough, this number here will always be the same as this number here, because we're asking for the end of the trough. So wherever the water, whatever the depth of the water is, that's how tall the section we're talking about is. In the previous example, the plate was under the water, which is not the same situation we have here. Okay, so let's say, I guess I can make that 1960 and a 0 times y times 0.5 minus y dy. Well, you know what? Actually, I'll do this. It's a minor difference, but I think it's going to be slightly easier if I distribute differently. If I distribute this 2 onto this guy and get 1 minus 2y, that will be, I think, maybe slightly easier. So 9,800 times 1 minus 2y times y dy. Not a big difference, but maybe a little bit easier for us. So I'll move the 9,800 out front. And then distribute the y, so y minus 2y squared dy. So this will be 9,800 times y squared over 2 minus 2y cubed over 3. I'm starting to think this didn't really save me any trouble as far as having that 2 there. 0.5. So this will be 9,800 times 0.25 over 2 minus 0.25 over 3 minus 0. So, well, that's going to be 0.75 over 6 minus 0.5 over 6, so 0.25 over 6. Yeah, that's right. That's going to be not a very clean number, so I'll just get a decimal approximation and not worry about, oh, how does this simplify? So 9,800 times 0.25 divided by 6, and I get, well, I guess I am, 1225 over 3 is exactly what it is. Of course, this is in newtons. But if I want a decimal approximation, I could say this is about 408.333 newtons. Okay, so there's how you find the force on something that is not merely just a rectangular plate. That's relatively simple if you use the center of that. Later on, we are going to see ways to get around some of this, and using the center as kind of a hint. Like, what's the center of a triangle? That's something we'll get to in the next section, 4.6. No, 2.6, sorry, 2.6.